In this video, we're going to talk about relative rates of growth. So we have two functions, f of x and g of x. They're both positive for x sufficiently large. We say that f grows faster than g when limit of f of x over g of x as x approaches infinity and equals to infinity. And we say that g grows slower than f as x approaches infinity if g of x over f of x as limit of x approaches infinity goes to 0. And we'll talk about more about what you mean by growing faster and growing slower of functions. So let's see what happens when we do limit as x approaches infinity of natural log of x over x. When you do that, you get infinity. Natural log of infinity is infinity. And as x goes to infinity, that goes to infinity as well. So we get infinity over infinity, which means we could apply Hopital's rule. So you get limit as x goes to infinity. You get 1 over x. And the derivative of x is just 1. So this is just the same thing as limit as x goes to infinity, 1 over x. So what happens as x goes to infinity? You get 1 over infinity, which is 0. So based on this conclusion, you know that natural log of x is growing slower than x. Now what happens when you put x on top and natural log of x on the bottom? When x goes to infinity, you still get infinity over infinity. So we could apply Hopital's rule. You get limit as x goes to infinity. Derivative of x is 1. Derivative of natural log of x is 1 over x. When you simplify that, you get limit as x goes to infinity of x. So equals to infinity. So this means, based on this, x is growing faster than natural log of x. So in the last example, we saw that natural log of x grows slower than x. In this example, we saw that x grows faster than natural log of x. So let's look at it graphically, how natural log of x and x behave. So we have graph of natural log of x, and we have graph of y equals x. As you can see, as x approaches infinity, look at the y value of natural log of x. It's approaching infinity very slowly, isn't it? As x gets bigger and bigger, the y value is getting bigger and bigger very slowly. What about y equals x? As x goes to infinity, look at the y value. Y value is approaching infinity. But notice the difference between these two graphs. I mean, as x goes to infinity, they both go to infinity. However, look at the y value of both of them when they have the same x value. Y equals x has a higher y value than the natural log of x as x goes to infinity. So when we say something grows faster than the other, just compare the y values as x goes to infinity. Which one has the higher y value than the other? That's why we say x grows faster than natural log of x, or natural log of x grows slower than y equals x. So what do you think is going to happen when we have limit of x squared over e to the x as x goes to infinity? Well, they both go to infinity, so you might say, I'm going to use Hopital's rule. Yes, that's one way of doing it. But let's think about these two functions. X squared is a polynomial, and e to the x is exponential function. So which one grows faster as x approaches infinity? What do you think? Well, let's take a look at graphs. So I have e to the x, an exponential function, and I got y equals x squared. As x goes to infinity, right, which one grows faster? It looks like e to the x, because with the same x value, e to the x has a higher y value. Notice, no matter what x value you have, by the way, as x goes to infinity means as x gets bigger, it doesn't matter how it behaves in the beginning, but as x gets bigger, which one will eventually have higher y value? It's going to be e to the x. So e to the x grows faster than x squared. Since e to the x grows faster than x squared, this will end up equal to 0 because the bottom grows faster than the top. However, if it was like limit as x goes to infinity of e to the x over x squared, now it's going to go to what? Infinity, because the top grows faster than the bottom. Now here's the important concept. Whenever you have a polynomial like x to the n power, where n is a positive integer, and you have a exponential function a to the x, where a is a positive real number such that a is not equal to 1, exponential will always grow faster than any polynomial. So for example, let's say you got x to the 10 plus 5x to the 9 plus 5x plus 7. Let's say this is a polynomial, and let's say you got 3 to the x. Eventually, as x approaches infinity, 3 to the x will grow faster than this polynomial over here. What if they're both exponential and they have a different base? Which one grows faster? Well, if they're both exponential and with the same exponent, the one with the higher base than the other will grow faster. So let's say you got limit as x goes to infinity of 2 to the x over 5 to the x. And you know that it will go to 0 because 5 to the x grows faster than 2 to the x. And if you have a limit as x goes to infinity of 5 to the x over 2 to the x, that will go to infinity because 5 to the x grows faster than 2 to the x. Now what if you have a limit of this? You got 3x to the 10th power minus 8x squared plus 5 over 4x to the 10th power minus 9x to the 5th plus 7. What happens as x goes to infinity? Well, notice the degree on the top and the bottom. They're same, isn't it? It doesn't matter what comes after. So it's going to be, I mean, you could try Hopital's rule many times. You end up getting 3 over 4. How do I know that? Look at the coefficients. It's 3 and it's 4, and they have the same degree. So when this happens, when you get a finite and not 0, we say that these two grow at the same rate, which is this right here. So when you have two functions, f and g, and as x goes to infinity, and you get a finite number that is not equal to 0, then we say that these two functions grow at the same rate. So here's the order of how it grows. You have natural log of x, right? The polynomial will grow faster than natural log of x, and the exponential grows faster than polynomial, and the x factorial grows faster than a to the x, the exponential, eventually as x goes to infinity, and x to the x, it grows faster than x factorial. So if you have something like, let's say, limit as x goes to infinity of x factorial over x to the x. You know that it's going to go to 0 because x factorial grows slower than x to the x.